I am Brian Howe, an acoustical engineer at HGC Engineering. Through these video series, we have been answering questions from our clients and submitted through our website. Today's topic is how do you assess and control vibration impacting sensitive instrumentation and equipment? Vibration can negatively impact sensitive processes and equipment, whether it's caused by trains, machinery, or even footfalls, by distorting images, and in the worst case, obfuscating or ruining electronic circuits. In today's presentation, we'll be briefly going over some examples of sensitive instrumentation and processes, discussing typical vibration criteria, assessment methodologies, and finally, mitigation strategies. There are many examples of vibration-sensitive instrumentation. We'll be touching on a few. Scanning electron microscopes are a good example where vibration can distort the image. In the case of magnetic resonance imaging machines, whether in hospitals or for test samples in laboratories, the situation is a little bit more complicated because the images are produced through a mathematical function, so there's not a linear relationship between vibration and distortion as there would be in the case of microscopes. Ultrafine lithography is a good example of a sensitive process in the semiconductor industry. Lithography produces patterns on wafer chips, and the vibration impact can distort these patterns to the point that the chip becomes rendered essentially useless. Several criteria can be used for assessing vibration on sensitive equipment. Generally, they follow an amplitude of the vibration, whether that's in displacement, velocity, or acceleration, as a function of frequency in units of cycles per second or hertz. The stringency of the vibration criteria is often related to the cost of the process. For example, distortion of a scanning electron microscope image due to the passage of a train may be easy to redo. However, with an automated process such as DNA sequencing, even minor vibrations can destroy that. Of course, there are other medical procedures that are also highly sensitive vibration, such as that impacting the microscope for eye surgery. The most reliable vibration criteria normally comes from the manufacturer, developed through either testing or field experience. Often there are amplification of certain vibration of certain components in the system. If you think of the amplification of an arm supporting a microscope eyepiece or the stylus of a coordinate measuring machine, the manufacturers typically introduce damping and other measures to control that, but nonetheless the vibration criteria can be more sensitive at those frequencies. Generic vibration criteria started to be developed in the 1960s in the aircraft industries, and has since gone on to be refined for other laboratory and electronic industries. Now commonly known as the VCA, VCB, all the way up to VCG limits, which are in practice difficult to achieve. These vibration criteria have now been referenced in ISO standards and in the design guidelines for the Canadian and American Institutes of Steel Construction. The most common method for assessing vibration is through measurements using seismic accelerometers and real-time frequency analyzers. The data is often used by itself or as input to a finite element analysis program. FEA is a mathematical methodology to be able to predict the response of a structure to vibration and also explore mitigation options. Once a potential issue is identified, mitigation needs to be considered, starting usually with the foundation or of the machinery itself. This large spread footings, concrete spread footings, can reduce vibration, as will large concrete caissons, particularly if you can get those caissons to extend down to bedrock. Other structural modifications can be achieved, whether that's with mass, stiffer beams, or damping techniques. There are a host of vibration isolation mounts for supporting sensitive equipment. As a rule, the performance of the mount increases as the static deflection of that mount increases. So for high frequency vibration, rubber or polyurethane pads may be sufficient, whereas in cases where high low frequency attenuation is required, we generally get into steel or air springs. Very flexible systems are not without drawbacks, however, as the impact of being bumped by the instrument operator or vibration developed within the machine, such as a high-speed coordinate measuring machine, can cause issues. In those cases, it's important to have an adequate concrete or steel inertia base for the machine and/or damping. When passive isolation systems prove insufficient, consideration is then given to active vibration control systems, wherein sensors and electric, pneumatic, or hydraulic actuators controlled by a processor counter the vibration. Although more expensive than passive isolation systems, these active systems are also can control both vibration feeding into the instrument from outside and vibration produced by the machine itself. In conclusion, to help ensure the performance of vibration-sensitive instruments, it is important to assess and control vibration. We've gone through some of the highlights of that here, of what is really quite a complex matter to deal with. So that is our topic for today. We hope you've enjoyed it. If there are any other questions that you would like us to address, please let us know. In the meantime, we look forward to seeing you again. Bye for now.